In the last lecture, we have seen the Cartesian coordinate system. Now, in this lecture, we are going to see the cylindrical coordinate system and its relationship with the Cartesian coordinate system. So, let us start the cylindrical coordinate system. The cylindrical coordinate system. This type of coordinate system is very important whenever we are dealing with the problems having the cylindrical symmetry. So, here the cylindrical coordinate system is given by this diagram. You can see that the x, y, z it is representing the Cartesian coordinate system, but the cylinder, the part of the cylinder which is representing here is the cylindrical coordinate system. In this coordinate system, just like the Cartesian coordinate system, we have three axes. One is r, another is phi, and the third one is z. And its ranges, you can see that here r varies from 0 to infinite. Here we will discuss afterwards what is r, what is phi and z. So here r, you can see that it starts from the z axis and it is perpendicularly, it will move in this direction, and it is one of the axes of the cylindrical coordinate system. The other axis is phi, which will vary from 0. Here in the, it starts from the x-axis, and it will vary, and it will vary up to 2 pi, that means 360 degree. And z will vary from minus infinity to plus infinity, as we have seen in the case of Cartesian coordinate system. So now suppose we have a point P on this surface of the cylinder or surface of the cylindrical coordinate system. Now we want to find out the distance vector from the origin to the point P. So this point can be represented in cylindrical coordinate system, just like we have represented the point in Cartesian coordinate system in x, y and z axis. Here we will represent the point P or the distance vector r from the origin to the point P in this coordinate system using r, phi and z. Here, what is r? R is the radius of the cylinder passing through the point P. Here, r is the radial distance from the z axis, and which is passing through the point P. And the unit vector, if we draw here, it will start from this point P and it will follow the path in which the r is moving. Next is the phi. Phi is called the azimuthal angle, and the phi can be measured, which must be measured from the x-axis and on xy plane. Here phi is the azimuthal angle, and z as same as the Cartesian coordinate system. So if we have these three coordinate axes, that is r, phi and z, then it will be easier to describe any distance vector or the position vector in this cylindrical coordinate system that we will see here. So here the component of vector p, that means from the origin to the point P, we are considering the vector distance vector p, and its component can be written as just like the Cartesian coordinate system, that is pr, p phi and pz. If these are the three components of vector p, then it will be easier to define the position vector p, that will be equals to pr ar plus p phi a phi plus pz az. You see that pr, p phi and pz are the components of vector p along the direction of r, phi and z, and ar, fi, az are the unit vector, and which will be in the direction of r, phi and z direction. Now, as I said earlier, ar, fi, az are the unit vectors. in r, phi and z directions respectively. So now say any vector A can be represented in cylindrical coordinate system, just like we have seen the Cartesian coordinate system, the representation of any vector, a position vector in Cartesian coordinate system. Here also we can define a position vector in cylindrical in this coordinate system easily. Say this vector A can be represented by this equation. You can see that the A vector A will be equals to AR Fi plus AZ. Here capital AR, Fi and Az is representing the components of vector A along the r axis, phi axis and the z axis. And as I said earlier, AR, Fi and Az are the unit normal vectors along r, phi, z direction respectively. Now here one point to be noted, here the A phi is not in degree. The phi is in degree but A phi is not in degree, because A phi will be the tangential or tangent on the point P. So here A phi is not in degree. Now as the vector A is a vector, so we can find out the magnitude of vector A. Here the mod of A will be equal to root over of AR square plus Fi square plus Az square. Here we can see that the unit vectors AR, Fi and Az are mutually perpendicular because our coordinate system is orthogonal. So from the diagram also we can understand, that the AR, Fi and Az are mutually perpendicular. So now we are going to see the cross product and the dot product of the unit vectors. Here the cross product, to find out the cross product, as we have seen the unit circle in the case of Cartesian coordinate system, here also we are going to use the unit circle. Here it is the unit circle. This here we are representing AR, then Fi, then Az, and we are moving in the anti-clockwise direction. If we move in the anti-clockwise direction, then we can find out AR cross Fi will be equals to Az, Fi cross Az will be equals to AR, and Az cross AR will be equals to Fi. Now if we move in the clockwise direction, then we can see that AR cross Az will be equals to minus Fi, just like the Cartesian coordinate system. Az cross Fi equals to minus AR, and Fi cross AR will be equals to Az. Now the dot product of these three unit vectors can be calculated. You see that AR dot AR. AR dot AR means in the same direction, AR, both the AR will be in the same direction, so theta will be 0, so cos 0 will be equals to 1, so AR dot AR will be equals to 1. Similarly, we can find out Fi dot Fi will be 1, Az dot Az will be equals to 1. And if we want to find out the dot product of AR dot Fi or Fi dot Az or Az dot AR, then we know that this is the orthogonal coordinate system. So AR Fi will be at 90 degree, the angle will be at 90 degrees, so in cos 90 is 0, so it will be 0. So all the portion will be 0. Now we are going to see the relationship between the components of Cartesian and the cylindrical coordinate system. Now in the first lecture we have discussed that why we need to study different coordinate systems. So there and why we need to transform the coordinate system from one coordinate to the another coordinate. So that is why here we are going to see how to transform the problem in one coordinate system to the other coordinate system. Now if we divide, or if we find a resolve the vector r, we will see in the next PPT or next page the diagram. Here we are going to consider the vector r, which is divided or which is decomposed or resolved into two axes, that is x and y. Then what we will get, x equals to r cos phi and y equals to r sin phi. Let us see that how we are getting that one. Here you can see that the x, y, z is the Cartesian coordinate system. On that coordinate system, we have taken a point P, which is represented by P, which is the function of x, y, z. And this point P also can be represented in terms of the cylindrical coordinate system, that is P equals to The P is the function of r, phi and z. Now, the r is the radial distance, as I said in the earlier diagram, radial distance from the z axis to the point P. Here you see that this is the point P here. So, this is the radial distance. Now, if we resolve this r along the x direction and the z direction, what we will get? X equals to r cos phi. Here you can see that x equals to r cos phi. Similarly, we can get y equals to r sin phi and z will be same, z equals to z. Now, we can see that if the z, phi and r is given to us, then we can transform the problem into the Cartesian coordinate system by this relationship, that is we can find out x, y and z. So, this is the transformation from cylindrical to Cartesian coordinate system. Similarly, if the parameters, that is x, y and z are given to us, then we can find out from that r, phi and z. Similarly, this is the relationship. Here you can see that the transformation from the Cartesian to the cylindrical coordinate system. Here r, we are going to find out r will be equals to root over of x square plus y square. Here you can see that. So, if x and y is given, r we can find out. Similarly, phi can be, we can find out phi, that is if y and x is given, and z will be same. So, z in Cartesian and cylindrical coordinate system will be same. So, this is the relationship, that first relationship. From that we can find out if the problem is given in cylindrical coordinate system, then we can transform that one in Cartesian coordinate system by this formula. And if the problem is given in Cartesian coordinate system, then we can transform the problem in from the Cartesian coordinate system to the cylindrical coordinate system by this formula. Now, we are going to find out the relationship between the unit vectors. So, here we have it is from the simple geometry we can find out the relationship between the ax, ay, az and ar, fi, az. Here we are going to see that. Now, you see that the first diagram, you see that here in this diagram we have taken only the xy component, the 2D diagram, that is xy. If you look at the top, if you look from the top of the previous diagram, then we will get this type of diagram. Here you see that the x and this is y, and this is representing, this dotted line is representing the r vector, and that point, this here, this point is representing the point P. Now, if this is the point P, then the unit vector will be along the r direction. So, this is the unit vector AR. Now, we are going to find out the component of AR along the x-axis. To find out, we have drawn here the blue line. You can see that the parallel axis, which is represented by the AX, that is the unit vector AX along the x direction here, and this is phi, because this one is the phi angle. So, this will be also phi. It is simple geometry. So, if we got this phi, then it will be the component of AR along the x-axis AX will be equals to AR cos phi. So, here the component of AR we got, that is on the AX, that is cos phi AR or AR cos phi. Now, we want to find out the component of phi, Fi, component of Fi along the x-axis. To find out this, suppose this is the point P here. So, if this is the point P, the radial distance of Fi, the radial distance is AR. So, Fi will be tangential, this is the point P, and if you draw here the circle, the tangent will be in this direction, in this direction. So, this is because it is the orthogonal coordinate system. So, AR and Fi will be at 90 degree, but here we are taking the minus Fi direction. Here, if Fi is in this direction, so 180 degree, if the phase difference is 180 degree, so in the opposite direction it will be minus Fi. Now, we want to find out the component of minus Fi along the x direction. So, here you see that this AR and Fi, minus Fi is at 90 degree. So, this angle Ax and minus Fi will be 90 minus 5. So if this is 90 minus phi, then what we will get? That is minus of Fi cos 90 minus phi, minus of Fi cos 90 minus phi. So from that we will get minus of sin phi Fi. So here we can see that and there is no z axis component, so that is why we have the Ax, the unit vector Ax, that is related with the unit vectors Ar and Fi by this equation, that is Ax equals to cos phi Ar minus sin phi Fi. Similarly, from the second diagram, we can find out the expression or the relationship between the Ay and Ar Fi. You see that this is the Ay unit vector along the y direction. So this is this blue line I have drawn here. We have drawn here. This blue line is representing the unit vector Ay. Now, as I said earlier, this is the vector r, this is the x axis r. So here unit vector is ar and it is a phi, and this one you see that the ay. So if this is phi, then if we draw x axis here, then it will be phi. This is, then this angle will be 90 minus phi and this angle will be phi. So if this angle is phi, then we can represent the component of a phi along ay, that is ay equals to a phi Fi cos phi. So here cos phi Fi we got. Now if we want to find out the component of AR along AY direction, so here we will get this is 90 minus phi. So the component of AR will be equals to the sin phi AR. So if we add these two components along AY, so we will get AY equals to sin phi AR plus cos phi Fi. And as again I say that Z component is not present here, so AZ will be equals to AZ. Similarly, in this, from this expression, we know that if AR, Fi and Az is known, then we can find out Ax, Ay, Az. Similarly, if Ax, Ay and Az is known, from these two diagrams we can find out Ar, Fi, Az. You see that Ar equals to cos phi Ax plus sin phi Ay, Fi equals to minus sin phi Ax plus cos phi Ay, Az equals to Az. From these two diagram also we can find out, because if AR, now we want to find out, suppose this one we are taking this one AR, we want to find out the component of AX and AY along AR. So this is AR, so component of AX along AR, it will be cos phi AX, this is AX, so it is cos phi AX, and component of AI, from that we can find out that will be, you see that this is AY component of AY along AR, that will be sin phi AY. So from that we can get AR. Similarly we can find out A phi and AZ. Now we got, finally we have the relationship between the components of Cartesian and cylindrical systems of vector A can be written as, now you see that here the components of A is related in Cartesian coordinate system to the cylindrical coordinate system we have seen. Also we have seen the unit vectors, the relationship between the unit vectors of the Cartesian coordinate system and the cylindrical coordinate system. Now we are going to represent this expression. You see that in Cartesian coordinate system, A equals to Ax plus Ay plus Az. Now this Ax, unit vector Ax, unit vector Ay, unit vector Az is replaced by these parameters, because these expressions, because these expressions we got from the cylindrical coordinate system, the relationship we have seen here. You see that Ax equals to this, Ay equals to this, Az equals to this. So that we are going to put in this expression here. So we have written here Ax is represented by this, Ay is represented by this, and Az will be, unit vector Az will be same as the Cartesian coordinate system and the cylindrical coordinate system. Now rearranging this, all the terms, we will get these components, that is component Ax cos phi plus Ay sin phi, because here Ar is present, here Ar is present. If we simplify this, then Ax cos phi plus Ay sin phi, Ar and AR will be common. Similarly, we will get this, and finally we can write this term equals to the component AR into unit vector AR plus this term is the component FI into unit vector FI plus AZ. So now AR it will be equals to this term. So AR Fi will be equals to this term. So this term I have written, and Az will be equals to same. Now in matrix form, these three equations can be written. Here you can see that AR Fi Az that will be equals to cos phi sin phi 0 minus sin phi cos phi 0 and 0 0 1 Ax Ay Az. If you find out, if you simplify this one, then AR will be equals to cos phi Ax plus sin phi Ay plus 0. So that equation is valid. Now Fi equals to same. Fi equals to minus sin phi Ax. Here you see that plus cos phi Ay, this one, and the 0 into Az will be 0. So this term is valid. So Az equals to 0 into x 0 plus 0 into Ay 0. Az will be equals to Az here. Now this is the form, if you remember, then it will be easier to transform one problem from the Cartesian coordinate system to the cylindrical coordinate system. You see that. But if the problem is given in cylindrical coordinate system, we want to transform that into the Cartesian coordinate system. From this matrix form, we can find out the expression. This is same. You see that Ax, Ay, Az, which will be equals to inverse of this. You see that the inverse of this expression into AR Fi Az. So here from this expression, if AR Fi Az is given to us in the problem, then we can find out the components in Cartesian coordinate system Ax, Ay, Az using this matrix form. So this is the relationship between the components of the Cartesian coordinate system and the cylindrical coordinate system we have seen, and also we have seen the relationship between the unit vectors of the Cartesian coordinate system and cylindrical coordinate system. Thank you very much.